So now let's consider this wave traveling in this direction and imagine what it does to a charge. Let's suppose I have a small positive charge here, and that positive charge is in a slightly resistive medium. The reason for the resistive medium is so that this moves in time with the electric field. In other words, so the electric field will be proportional to the velocity rather than just to the acceleration. If it's a totally free isolated charge, the electric field will move in time, or the acceleration will be proportional to the electric field. But if there's a little bit of other force, a resistive force, and that becomes dominant, then the velocity will match the force, just like if you're moving through water, the resistance of the water makes the velocity match the force. Okay, so this is going to move up and down in time with the electric field. So that's how it gets pushed by the electric field. But if it's moving, then we experience a force due to the motion from the magnetic field. And to find that, we're going to use the right-hand rule. So at one moment, when it's here, it's going to be moving up. So the velocity is upward. And then we know the force from a magnetic field is equal to QV cross B. The charge is positive, the velocity is up. We imagine our fingers with our thumb out this way and fingers like that. Excuse me. If my thumb is to the left and my fingers are up like that, you'll notice I can't bend my fingers into the direction of the magnetic field. So instead, we have to turn our hand around so that it's palm out, thumb to the right. Hold your hand like that, and you'll notice that you can easily bend your fingers from the knuckles out into the direction of the magnetic field here. And your thumb will point to the right. That means that once the electric field starts things moving, the magnetic field will cause a force in the direction that the wave is propagating. In other words, the wave does in fact carry with it some momentum. And that momentum will create a force to the right, and that force is proportional to the intensity, and it's a force per unit area, so it's a pressure. Now, if the wave is being absorbed, then the pressure exerted by the light hitting the surface is just the intensity divided by the speed of light. If it's reflected, then just as in the case of a ball hitting a wall, remember, if a ball hits a wall and bounces back, then the change in momentum is 2mv. So if the light comes in, hits a surface, and reflects backwards, then the change in the intensity of light is more dramatic. Instead of just going from rightward to zero, it goes from right back to left. And that results in twice as much radiation pressure. You will note, because this is divided by C, that's a fairly small amount of pressure. So if we look and thought, for example, there's about 1,000 watts per meter squared of energy hitting the Earth, and that's a fairly significant amount of energy. If we asked the pressure, that would be the intensity divided by C. That's 1,000 watts, or Newton meters per second meter squared, divided by 3 times 10 to the 8th meters per second. You'll notice meters cancels, seconds cancels. It's newtons per meter squared, but this is only going to be 3 times 10 to the negative 6 pascals. That's a very small amount of pressure when you consider that atmospheric pressure is 100,000 pascals. So this is 10 to the 11 times smaller than atmospheric pressure.